into n to the power 2, okay, that are going to be related to trigonometry. That is
A
all
very good evening to all of you.
right. That's going to be 1 by 3,
Am I audible to you people?
3 by 9, right, and so on, right? What is the better way to represent this? N comma 3n
Can you please let me know
is a
any one of the participants? Am I audible to you? Okay, all right, thank you. So, welcome to our third webinar of this series of Physics 12th CBSE one shot revision, right? So, today we'll be discussing, as you can see on your screens, I think the screen is being shared, right?
they are only A and B will only be related if A minus B, modulus of A minus B.
All right.
A minus
So, today we'll be discussing electrostatics and current electricity, right? So, these are the initial units we have in our physics syllabus 12th.
this class of 2 as well. So try this question, everyone. Come on.
All right. So, you see, let us discuss about electrostatics and current electricity. So, in electrostatics, what we have, so we have two chapters, right? We have electric charges and fields, right? We have electrostatic potential. In the next presentation, I'll be discussing the marking scheme, the syllabus and all, right? So electric charges and fields, we have electrostatic potential and capacitance. So these two chapters we have, and these two chapters, as per the marking scheme of 2024-25, so these two chapters combined will be of 10 marks, right? So this would be of 5 and this would be of 5, right? So accordingly, we need to prepare. And as we have already discussed in our first webinar, that this chapter has a lots of derivations, right? So this chapter is important from the derivations point of view, right? So we'll be discussing what are all important derivations we have in this unit, electrostatics, right? The next unit we have is of current electricity. This chapter, as per CBSE, has this weightage of 6 marks, right? And there are lots of deleted portions from this chapter. For example, previously there was meter bridge, right? Potentiometer was there 2 years back, then it was deleted, and this year we don't have even meter bridge, right? So up to Wheatstone bridge only we have the in the syllabus, right? So as I've already told you that you need to focus upon at this point of time on the key concepts, right? You need to figure out what are the key concepts, and that we'll be discussing. We have already discussed about the modern physics in our last webinar. So today we'll be discussing about the key concepts, right? And I'll be making sure that you'll be able to see those concepts, right? I have made a presentation so that you'll be able to have a quick recap of all the concepts, right? So the key concepts we have in electric charges and fields, right? So let me just make you remember that it is first Coulomb's law, right? And in Coulomb's law, I have already told you many times, this question has already come in previous year papers. Coulomb's law in vector form, right? So Coulomb's law in vector form, right? So this is very important, right? Coulomb's law in vector form, right? And So this might come in 3 marker, right?
Yes, come on everyone,
So this is
fast.
important. You need to know that, right? Some conceptual questions also arise from this chapter, Coulomb's law, as we'll be looking at from the previous paper of 2024-25, right? How Coulomb's law is related to its relation with the electric field due to a point charge, right? So these two are the subtopics from this Coulomb's law topic that we already have got questions in the previous year, right? And in CBSE, questions generally get also repeated, right? So you must get hold of these two subtopics in Coulomb's law, right? The definition part, obviously, you must be knowing. All right. So then we have electric field, right? The normal definition due to a point charge is obviously you already know. I think I am audible now. Right, right. So the diagram part of it, right? The questions might arise of the electric field lines, right? You need to draw the diagram and also the electric field due to multiple charges, right? Multiple charges. So I'm talking about the key concepts from this particular chapter, right? So that you must be keeping in mind, right? You must be studying about it before you exam, right? So the normal part, the electric field due to point charge, so you must be knowing, right? The multiple charges you should keep in your mind. And from this only arises the superposition principle, right? That's why it becomes important. Superposition principle, right? It may ask that how superposition principle is applied in calculating electric field due to multiple charges, right? And then obviously we have electric field lines. So the properties of electric field lines might come. Properties must be getting hold of the properties and the drawing of electric field lines, right? The diagram part of it that you must practice, right? The electric field due to a point charge, plus or minus, the electric field due to the electric field lines due to a dipole, that becomes important. Electric field lines of a dipole, and also let's say two like charges placed at a distance. To like charges, for example, plus and plus. In dipole we have what? In dipole we have plus and minus placed at a distance, right? To like charges means two positive charges are placed at a distance and you need to draw the electric field lines, right? This question might arise in 3 marker electric field lines question will come, right? All right. So derivation is not there up to electric field lines, but yes, in Coulomb's law this vector forms derivation is important, right? It's not a derivation, but it's a representation of Coulomb's law in vector form, right? Right. Now coming to the very important part that you will have a question, right? It's 100% you will have a question from this topic, that is electric dipole, right? Very, very important. You will get at least of 5 marks from this particular topic, electric dipole from electrostatics. So this is the core topic of this chapter, right? You must spend time in this like accordingly. So electric dipole, and this is very important from the derivation point of view. This electric dipole, you need to find the electric field due to a dipole, right? As we have already discussed in the first webinar also, that electric field at axial point and at equatorial point, right? That I'll be telling you in the coming presentation, right? So very important from the derivation point of view, this electric dipole, right? Derivation part of electric field and also this concept of torque associated with it. When electric dipole is placed in a uniform external electric field, the torque part of it and the potential energy part of it, right? So these three things, no, the derivation of electric field, the torque, the potential energy part related to the electric dipole, right? And in the next chapter, the electrostatic potential, you will have potential due to electric dipole, right? So let's take it as a combined topic of electric dipole. The potential also you need to calculate, right, due to electric dipole. So these, from these topics, you will have, right, at least of 5 marks paper, right? 5 marker also may come, right? And a derivation and an associated numerical, right? Numerical from the torque part, numerical from the potential energy part, right? It might ask you about the stable equilibrium, right? The unstable equilibrium, right? In the case of electric dipole placed in a uniform electric field. Yeah, are you getting it? Can you please respond? Are you getting it?
Yes, sir.
I'm right. I'm putting across the significance of this topic, right? The electric dipole, right? So you must be spending a lot of time. Don't worry about, let's say you are not very much comfortable in Gauss law, right? And it is also easy, right? Gauss law is also easy, but let's say you're not very much comfortable. So at least spend time, right? Write 2 times, 3 times these derivations associated with electric dipole, right? Will come, definitely come, right? Every year it comes. Okay. And also from this chapter, electric charges and fields, it's not written here. Yes, we have our very important topic that is known as Gauss law, right? Gauss law. So in Gauss law, it might ask you about the application of Gauss law. It can ask you the definition from the theoretical point of view, right? And then the application part of it. Its applications, right? Applications of Gauss law. So in applications, you will have due to a point charge, right? I'm just writing it. I'll be sharing the syllabus also, right? That what are the applications that are important, but just right now, I'm discussing that. In Gauss law, applications part is important. Due to a point charge, it may ask that apply Gauss law in calculating electric field due to a point charge, right? This is a very typical question, right? Which comes. And then we have due to an infinite wire, right? Due to an infinite wire, we have due to an infinite sheet, we have, right? Due to a spherical shell, we have. So these 3 4 topics only are there, right, in your syllabus, as CBSE, as far as CBSE is concerned, right? So these all are the important topics from electric charges and fields that you must be keeping in your mind, right? I'll be sharing with you the next presentation, which have a quick recap of these topics, right? So I'll just uh, run these slides very fast, and you'll just have a look on it, right? Just have a look at it. All right. Then coming to the electrostatic potential and capacitance. So as the name suggests, we have 2 parts in this chapter. One is related to electrostatic potential, right, and potential energy, and the associated potential energy of an electrostatic system, right, of a system having charges at rest. So what is the potential energy associated with it, right? So this part is there. And then we have the part of capacitance, right? Capacitance part is important, right? This is also important, but capacitance part is important. A question will come from capacitance also. It might come in MCQs, right? And in a numerical context, right? So capacitance is important from a numerical point of view, right? The combination of capacitors, that part is hold significance, right? All right. So in electric potential, electrostatic potential, you need to be very much precise about, you need to be focused about the definition of electric potential, right? So how is it, how this electric potential is associated with the work done, right? So it is work done per unit charge. And what is the difference between, right? What is the difference between potential energy and electrostatic potential? That difference you must be clear of, right? And what is the electrostatic potential due to a point charge, right? What is the formula for it, right? You must be knowing that. Can anyone tell me? Yes, can you tell me? Anyone? Mohammed, Ruhika, Sachi. Can you tell me the electrostatic potential due to a point charge at a distance r? Anyone? Right. Good, Ruhika. It's kq by r. Great. Right. So you must be knowing this at this point of time. It is kq by r. Right. And also in this electric potential also we have this calculation of electric potential due to multiple charges. So we have a point charge and due to multiple charges we have, and again this concept of superposition principle comes. So wherever there is multiple charges associated, right, we have this principle of superposition. So a related question might come, right? So mostly from this topic, electrostatic potential and potential energy, we get this theoretical type of questions, right? Okay. Then associated with this electric potential, we have this concept of equipotential surfaces, right? So many times in boards, it might ask you the concept of equipotential surfaces, right? So you must be clear of it, right? Equipotential surfaces. And then we have this relation between, right? As you might be aware of, this relation between electric field and potential, electrostatic potential, right? This E is equal to minus dV by dr, right? So this relationship also uh, you'll be revising. All right. Then we have this concept of capacitance, this topic of capacitance. Before capacitance, we learn about dielectrics, right? Dielectrics. So what are dielectrics? Dielectrics are insulators only, right? So what are dielectrics, right? What is dielectric constant? Can anyone tell me what is dielectric constant? You see if I am correct or not. Dielectric constant is denoted by capital K, and it is same as the relative permittivity of relative permittivity of a medium, right? Am I correct? Right. So that is the dielectric. All right. Can anyone tell me what happens if I have a, let's say, parallel plate capacitor, right? And its capacitance is C, and let's say I'll put a dielectric in between the parallel plates of it, right? In between this medium, in between this space, I'll put a dielectric, right? The whole space is filled with it, right? And this and its dielectric constant is K. So its capacitance becomes what? Now its capacitance would be C or something else. Can you tell?
So the capacitance decreases, right?
Capacitance decreases due to dielectric. Is it correct? I don't think so. Capacitance increases, right? We have this concept of dielectrics, right? Due to
Yes,
increasing
sir.
the capacitance only, right? We get dielectrics in the capacitance, this capacitance world due to for increasing the capacitance,
Sir.
right?
Yes, sir. Sorry.
Why? So this capacitance C dash new capacitance will become Kc, right? And this K is always greater than 1. Right? So that is why we say that if we put dielectric in between the spaces of a capacitor plates, the capacitance increases. Right? So the associated combination aspects, the associated numericals, you must be revising, right? Just from the NCRT level only, right? NCRT level is not very low level, right? So you must be having a very good concept of these numericals, right? So capacitance is there, right? So numerical point of view, this capacitance becomes important, right? It might ask you about the capacitance of a parallel plate capacitor, right? So parallel plate capacitor you must be focusing upon. Don't worry about the spherical capacitor. Don't worry about the cylindrical capacitor for now if you haven't read it yet, right? So just focus upon the parallel plate capacitor, right? And learn about the associated concepts. So I'm just telling you the key concepts, right? Parallel plate capacitor you must be focusing on. And then we have this concept of energy stored. Energy stored inside a parallel plate capacitor, let's say having charge Q. So can you tell me what is the energy stored? Just let's revise it. What is the energy stored in a capacitor?
L1 and L1. Okay, it is going to be parallel to
Can
itself,
anyone tell me the
right?
formula? It's
Like
half
that, right?
Half
CV
CV
square,
square. square.
right? Or we can do it by Q square by
Into L1
2C,
2C.
right? Also we can have another form. Can you tell me what is the another, what is the another form we can have?
Yes, and L1 if it is parallel to, let's say, L2, right?
What can be the other
And
form?
L2 is parallel to
Can I
L3.
say it is half
With that
QV?
means that L1 is going to be parallel to L2.
Right, good, Ruhika.
Right, everyone?
Good. Right,
Is
half
this my
QV.
point?
So this energy stored
This
part
I
is the last part of this chapter, right? All right. So I'll be also sharing you the quick notes, right?
that
All right. These are the formulae. You should be very clear about the formulae part, right? So in this chapter, in electrostatic potential, you see electric charges and fields, we have these derivations, applications, and related to electric dipole. One of them will definitely come. It might be possible that both of them will come in internal choices, right? In electrostatic potential and capacitance, there is as such no derivation involved, right? But yes, this parallel plate capacitance part you should be very clear of, right? So it might be there in the form of you can say he can ask that derive the formula of parallel plate capacitor, right? Or what is the formula of, so you have to just represent it. There's no kind of derivation involved, but you kind of represent it, right? The capacitance part. All right,
now
so you must be very clear about the formulae and derivations, right? So I advise you to write them down, right? Somewhere write down the derivations of electric field due to dipole, applications of Gauss law somewhere, right? And you just need to revise it at the last minute, right, before your exam. And the important formulae that you must be having in your a very one page, right? One page, on in one page only you can have your notes, very short notes. All right, then coming to current electricity, right? In current electricity, what are the important concepts we have? So in current electricity, firstly obviously the concept of current, right? Current is there. And in your 12th, this is concept of drift velocity becomes important,
right odd function
right?
in a piecewise manner,
So
right?
what is drift
You have
velocity?
to write it in, then
It will not ask you the derivation of drift velocity, so you need not worry about it, right? You just be knowing about the concept of drift velocity. What is drift velocity, right? So there is derivation also in NCRT, but it will not come, right? So drift velocity. Then we have this concept of current density. Current you have already studied in your 10th class. It will not ask again what is current. It will ask you the different physical quantity associated with that, that is current density, right? Associated with this J. Can you tell me relation which relates current density and drift velocity? Very important relation. Many times numericals come,
how do we 1 1
which relates this J and VD. Can you tell me?
tell me?
Anyone? Anyone from the participants? We have a lot of participants today. Devarsh, Amran, can you tell me?
Also, you can do that. You can find the range of this, right? But it is going to be really very far, right? Everyone?
Harshita,
Because you are already considering this as a piecewise function. You find the range, and it is going
you
to
need
be
to be interactive, right? You must have already revised it, and if you haven't revised it, just revise it now. Now you can have a book, now you can have your NCERT in front of you and you can tell from it, right? No problem, right?
The range is bigger than this. The range for this function.
So
the value is
that
going to be bigger.
formula is J is equal to, you must be remembering it now, NEVD.
Minus. It is already just written.
Do you know it or
Very
not?
simple. Okay, you just
Yes, good, Harshita. Very good. Very good. Yes, correct. J is equal to NEVD, right? And now what is J? J is current per unit area, right? NEVD. So now what is my current becomes NEA into VD, right? This is the formula of current which we should be knowing in our 12th class, right? V is equal to IR. Oh, okay, that is obviously you must be knowing it. You know it from your 8th class, right? So now you should be knowing this formula. I is equal to NEAVD or J is equal to NEVD, right? All right, right. Then in Ohm's law, then comes the Ohm's law part, right? On also one more important thing, there is one concept known as mobility, right? Mobility. Can anyone tell me the formula of mobility? It is denoted by mu, right? What is the formula of mobility? Can anyone tell? So you might feel this part of the electron electricity as a little complex, but you just have to know the formula. Very good, Harshita. Very good, right? Mobility is what? Mobility is right. Et by m also we can represent it with relaxation time also and all, but the main formula which is there is Vd by electric field, applied electric field, right? So per unit electric field applied, how much drift velocity the electrons are getting, right? That defines the mobility of the electrons, right? This mobility question is also important from the point of view of semiconductor electronics, which I have discussed in the previous webinar. In there, you need to calculate the mobility of electrons also, the mobility of holes also. But now we are discussing the electricity, the current electricity from the in the context of conductors, right? So we should be only knowing the mobility of electrons, because in conductors electrons are the only charge carriers we have, right? So Vd by E. Now we know the formula of Vd also in that formula is also important, the relaxation time one, right? That I'll be showing you in the next presentation, right, Ruhika, right? This one also is there, right? Okay, so mobility is important, right? Then comes the Ohm's law. In Ohm's law, what is there? No, he'll the exam will not ask you the definition of Ohm's law this time. This 2024 question also came just from the NCRT, right? So in Ohm's law, it will ask you the limitations of Ohm's law, that where Ohm's law is not valid, right? For example, in the case of this question is there in NCRT, this gallium arsenide it gave last year, right? The Ohm's law, the VI characteristics of this gallium arsenide, right? And it's from the NCRT. It's written line by line in NCRT, right? The limitations part, this is important, right? In Ohm's law. And then obviously we have this concept of uh, conductivity and resistivity. Conductivity, resistivity, and their dependence on temperature. Their dependence on temperature, right? Their dependence on temperature. So can you tell me, this question generally comes, right? If I'll increase the temperature of a conductor, so resistivity increases or decreases? What do you think? Anyone? If I increase the temperature of a conductor, the resistivity of it increases or decreases?
Increases.
The resistivity increases, right? Why is it so? Why the resistivity increases in a conductor?
Because relaxation time, mm, it increases.
Because the relaxation time increases. You see, what happens in conductor, as we increase the temperature, the motion of the electrons becomes more random. And when it will become more random, they'll collide more with the ions, right? They'll collide more with the ions, right? We have ions also, no, in the conductor. Electrons are free charge carriers, they can move. So their motion will become random and they'll collide more with the ions, right? So their relaxation time increases or decreases. What do you think? They'll be more relaxed or they'll be less relaxed. What do you think? So you revise it, right? So we'll be discussing it. I'll be showing you this. So the resistivity increases because of the randomness, the increase in the randomness of electrons. So what happens in the case of semiconductors? This is also the question from current electricity only, right? So how can they become more relaxed? You see, how can they become more relaxed? If I'll increase the temperature, right? They'll have more kinetic energy, no? They'll have more kinetic energy. They'll strike, they'll have collision more easily then. That is why the resistivity is getting increased, no? That is why the resistance is getting increased because they'll be colliding more, right?
Yeah.
So what happens in the case of semiconductors? If I increase the temperature, resistivity increases or decreases? In case of semiconductors, what do you think? What happens?
In semiconductors, it's the other way around.
In semiconductors, it's the other way around, right? Can you tell me why? So you might be knowing, you must be having this idea of semiconductors now, right? Because in semiconductors, what happens when we increase the temperature, the resistivity in semiconductors decreases, right? That means it becomes more conductive, right? It allows more current to pass through it on increasing the temperature. Why? Because semiconductors do not have free electrons, right? So there's no point of the increase in the randomness of their motion, right? They don't have free electrons. So when we increase the temperature, what happens? The the electrons in the which band? The valence band get enough energy to get into the conduction band, right? So in semiconductor, on increasing the temperature, we get more electrons for them to conduct electricity. So that's why we say that on increasing the temperature, the resistivity decreases. So these questions, the temperature dependence question, comes generally in two markers, right? With reason they come, right? That is why I'm asking you the reason part. With reasons they come. All right. Then we have this electrical power, right? Electrical power, the heating effect of current, right? These types of questions then come, right? Then we have Kirchhoff's laws, junction rule, loop rule, the circuit they'll give you and they'll ask you to tell the current in any branch, right? The voltage across any resistor or something, right? These types of questions, right? Series and parallel circuits will come. And in series and parallel circuits also, which series and parallel is important? Cells part, right? Now, not the resistors part is important. Cells with internal resistance. Cells with internal resistance, when they are combined in series, right? When they are combined in parallel, right? How they operate, right? How the dynamics change, right? That will be asked. So cells with internal resistance, so you should be knowing about it, right? And then we have this concept of Wheatstone bridge. Wheatstone bridge, right? So this you should be knowing about. So these are all the topics which we have. So I have told you, I have I have made your mind run through the various topics you need to be covering before your physics exam from these units. So this is 16 marks from this topic. So you just have this, because it is very easy to score from these topics because most of the part is derivations. So in 16 marks, 6 marks, 6 to 8 marks will come derivation only, right? Half of will be derivation only, and then some numerical, some theory. So you can say no. In 16, by how many types of questions we have in 16 marker, 8 marks, so you will have derivations only,
My voice is clear?
right? And mostly derivations will come from the dipole part and the Gauss law part, application part.
Yes.
And
So
then you
X
can
sum
say
of
that
X everything.
3 marks, right?
Yes.
3 marks or something. I'm just telling you an idea, right? 3 marks would be of theory, right? 3 marker or 4 marker would be of theory, you can say, right? And this theory might come in the form of 2 marker, might come in 3 marker, might come in MCQ or even MCQ also. This theory part will come. So 8 plus 4 is theory, right? Sorry, 4 is theory, 8 is derivations, and 4 you can say numericals,
Right. X2, X2 plus
right? On
X.
only these 3 types of questions you'll be getting in your exam, right? All right. Then I have already told you previous year questions are very important, right? So previous year questions you must study. Previous year questions you must be studying. I have told you in previous webinars also that try to at least, as you have limited time now, right? And I'm not giving you very vague ideas about that you can do 50 papers. No, you cannot do 50 papers. You have to revise also, not just doing. If you are doing, like for example, 2024-25 paper, right? So it will not be sufficient if you do it only one time. You'll have to revise it again, right? So I'll advise you that at least do very well, right? 5 papers, 5 previous year papers,
Basically is 1, 1, right?
5 previous year papers you
This
must do.
function is
And if you do 5 previous year papers, you will have a lot of idea about the, and you will not feel very different, right? You'll have a comfort when you'll be appearing in your final exams, right? You'll have a comfort level will come. Just be thorough with the NCRT, just be thorough with the topics which I have told you, the derivations and numericals and all. Stick to the examples also, and this NCRT examples which you have, no, i I tell every year students that NCRT examples are very important, more important than the exercises you have, back exercises. Because from NCRT examples, they give you direct questions
how will we do it in
in
the
the
exam?
exam. The NCRT examples and 5 previous year papers, right? I am giving you a very minimal, very like very practical target, right? Very minimal target I'm giving you,
Then the
right?
function is in
All right. So I'll be sharing you one more slide, right? So please wait.
X axis. Now, if we have to do the curve tracing, you remember how we used to do the curve tracing, but I think I have not taught you that. अच्छा curve tracing नहीं बताया ना मैंने किसी को पता है curve tracing anyone knows curve tracing how to do the curve tracing हाँ no anyway चलो I'll show you how the graph is going. So graph of this function everyone is going to look like this. So basically when we do curve tracing everyone, what we do is we first find the asymptotes, okay, the horizontal. First we find the derivative. We check if the function is going to be increasing or decreasing. यानी कि ऐसा होगा function या ऐसा होगा. Okay. Then we check the asymptote. So I know that the asymptote is going to be x is equals to 1 and x is equals to -1. Right. So and using the derivative, I know that the derivative is going to be 1 plus x plus 1 whole square or 1 upon x minus 1 whole
So I
square.
think
These
this
values.
is visible to you, the one-shot revision electrostatics and current electricity. Is it visible? Can you please reply?
Yes, sir.
Yes.
All right. So I'll be sharing you because we have just last 15 minutes left, 15-20 minutes left. So I'll be taking questions also. If you have any questions related to preparation or anything, it's I'm not saying that it must be related to the today's webinar only. If you have any question related to motivation or something, you can ask me at the end of the session, and I'll be sharing this PPT with you for you to revise it. Right? Just I have put it the various topics, right? So you see, we have electric charges, fields, and these 3 chapters we have discussed, right?
When x is
So
greater
what
than
would be
0,
this
it will
year's
be like
level
this.
of physics paper?
Okay, these are two
You
different
can
functions.
you can analyze the that's what I'm saying, that if you'll analyze the previous 5 year papers, you'll get an idea that only the average of it will come, right? It will not be very difficult, it will not be very easy even, right? So it will be an optimum level would be maintained as they have been giving since previous years, right? So previous year 5 year papers you do, you'll automatically have an idea of the level, right? And just be thorough with the derivations, be thorough with the theory part, because sometimes what happens, no, in numericals we might have our calculations mistake or something, right? And be thorough with the formula part, right? Even if you don't know how to solve a numerical, and if you know the formula, just write it down. Don't leave any question. Don't leave any question. That's I have been telling you uh, many
Now
times,
we
right?
put it on, right? In on to, whenever we are putting it on to a
So you
real
see, we have
we are going to find out the range of its function, right?
so these
So
this is
what
the
we
marks
need to
distribution we have, right? 5 marks, this 5 marks, this 6 marks, this, right? So this is the syllabus, right? So you must be very thorough about the syllabus. So this is syllabus from the electric charges and fields. You see, we have electric charges. Acha, you should be knowing in electrostatics the methods of charging, right? That I have not written here, right? Methods of charging is important. And I'm writing in electric charges. No, you'll have this concept of methods of charging. How many methods of charging we have? Can you tell me?
three, sir. Conduction, induction, friction.
Right. So three methods of charging. So you must be writing it down, right? Methods of charging we have conduction, right? Through contact. We can charge the body through contact, right? Like in the case of electroscope happens, right? Then we have charging by induction, right? Then we have charging by rubbing, charging by friction, as the the participant has said, right? So then conservation of charge. In conservation of charge, they might ask you about that how conservation of, like for example, charging by induction is there, right? Of charge is applicable there. So it might ask you a conceptual uncharged body with a charged body, right? You get this question in charging a uh, uncharged body with a charged body by contact. How conservation of charge is valid, right? So what you will say, that the charges, initial charges and final charges are the same. It has just redistributed itself, right? The charges have just redistributed themselves. So, and also the quantization of charge, right? Q is equal to any part, right? Q is equal to any concept, right? That's quantization of charge also becomes important, right? You must be knowing that. Then we have Coulomb's law, right? Then I've told you Coulomb's
Sir,
law, right? Yes.
any questions can be asked and related to mixing two chapters, like chapter one and chapter two together, they can ask, right?
No, 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 no. You need not worry about it. That comes in competitive exams generally, and that too in JEE Advanced, right?
Yes, sir.
So you cannot expect that in CBSE. They'll ask you simple and straightforward questions, right? So back sizes and the examples from NCRT are sufficient in knowing the level, right? They'll not combine conservation of charge with capacitance, let's say, right? They'll not do that, right? So then we have Coulomb's law.
Yes, sir.
uh, cool. Just I'm telling you, the presentation should be good, and you should be like presentation should be good, and don't leave any question, right? So Coulomb's law. Then we have force between 2 point charges, right? So that we have seen force between multiple charges, right? Superposition principle. This is important. Superposition principle. Many times questions come. So you have to mention that if you're calculating forces, if you're calculating electric field, electrostatic potential, to do multiple charges, you have to mention this keyword superposition principle, right? Then we have continuous charge distribution. So you must be knowing that how many continuous charge distributions we have. Can you tell me how many continuous charge distributions we have? We have linear, right? We have surface, we have volume charge distribution, right? You remember, I think, right? Then we have this electric field due to a point charge, electric field lines, electric dipole, very very important, electric dipole, right? I'm star marking, right? The topics you must be very aware of. Electric field due to a dipole, very important. Will come, question will come. Torque on a dipole, right? Then electric flux, right? This I missed out, I think, in the last presentation. So electric flux also, right? This is associated with the Gauss law only, but the general definition of electric flux, what it is, right? So with a diagram, you'll show a diagram, right? So always try to draw a diagram, right? If it is if you can, right? If it is possible, try to draw a diagram. Then Gauss theorem statements, applications, and you see how many applications are there in syllabus. This syllabus is, I have got it from the official website of CBSE, right? 2024-25. So only these derivations you must be focusing upon, and one of them will come. So I'm telling you, this electric field, this derivation, torque derivation. This is also derivation, right? Torque on a dipole. And this one third, application part. So infinitely long straight wire you'll be studying. Infinite plane sheet you'll be studying. Right? Sigma by 2 epsilon naught it comes, right? You remember, I think. Sigma by 2 epsilon naught due to an infinite plane sheet. And then we have thin spherical shell, right? Solid sphere is not in your syllabus. Solid sphere, non-conducting solid sphere is not in your syllabus. So you'll not worry about it. At this time, don't read anything apart from the syllabus, right? So derivations is very important. Got it?
So now let's take it forward. So that is going to become 1 plus.
Sir, which is like the most important derivation from the second chapter?
Second chapter, I'm telling you, right? So let's come to second chapter. We have electric potential, potential difference. What is potential difference between 2 points? Then electric potential due to a point charge, a dipole, a system. Okay, dipole. So electric potential due to a dipole, you must be knowing, right? There is a formula for it. Not derivation is important. They'll not ask you the derivation of electric potential due to a dipole. They might ask you, right? They might ask you, this derivation is important. You see, electric potential due to a electric dipole. This is important, right? This is important. You see, here also we find electric potential at axial point, and here also we find electric potential at an equatorial point, and then at a general point. Three parts are there, right? So at axial point and equatorial point, finding electric potential is important, not at general point. General points, only formula you remember, right? So this is important. Equipotential surfaces is important, the theoretical aspect of it, right? Then potential energy, you know, right? Potential energy, all right. Acha. Potential energy of electric dipole in electrostatic field is important. The formula we have is minus, you remember, vector P dot vector E, right? Minus PE cos theta. From here only we get this concept of stable equilibrium, unstable equilibrium, right? That might come, right? Derivation, as someone was asking, only electric potential due to dipole. That you must be knowing, right? Then we have dielectrics. What is electric polarization? Only theoretical part you can read, right? What is capacitance? What is capacitor? Then in numerical context, this combination of capacitors in series and in parallel, right? That is important. That becomes important, right? Then we have capacitance of a parallel capacitor with or without dielectric, right? Energy stored in a capacitor. It is written specifically, explicitly, that no derivation. So no derivation should be, you do not need to remember the derivation of energy stored, right? You just need to know the formula. Half CV square, Q square by 2C, half QV, right? So as far as derivation is concerned, only electric potential due to electric dipole derivation is important from this point, right? From this chapter,
Why I'm taking a union, everyone?
right? Then we have current electricity. In current electricity, you see this drift velocity becomes drift velocity, mobility, right? What is the relation with the electric current? Then Ohm's law. In Ohm's law also, I have told you VI characteristics of linear and non-linear, right? There's a topic in NCRT. You please read it. Always it is coming, right? Last year also it came. VI characteristics of non-linear wala part, right? The electrical energy power I have told you, electrical resistivity, conductivity I have told you, temperature dependence of resistance that I have told you. Then internal resistance of a cell. This becomes important, right? Questions, देखो, all are important, right? It's not that question will not come from temperature dependence. It might come, but internal resistance question will come, right? 95% chance, 99% chance. So internal resistance of a cell, right? Potential difference, terminal voltage. So what is the relation? You know what is the relation of terminal voltage? What is the relation? E minus IR. This relation they might ask you, right? A numerical might come from it. Then we have combination of cells in series, very, very important. This might come. Combination of cells in series and parallel, right? And then Wheatstone bridge, right? Meter bridge is not there, right? Got it?
That is what I think, right? So I think write it in a bit. Okay.
Now what is there? Now what I have done is, this is from our askIITians revision notes only. I have put some material, right? So this is a mind map. You must be knowing about it, right? So I have put mind maps also. So the team will share these two PPTs with you, right? The team will share this PPT. The team will share with you, right? So this all is written right on one page. Coulomb's law, electric field. You see the diagrams part of it. Then electric dipole, electric field part, torque part. Then electric flux, right? Then Gauss theorem, and then we have application of Gauss theorem, right? Application of Gauss theorem, you must be knowing it, right? So you see, I have written some of the things. So very fast, I am just running down the slides, right? You just have a look at it. This will be shared with you, right? So what is Coulomb's law? You should be knowing relative permittivity part. This relative permittivity I was talking about, that it is only the dielectric constant, right? What is epsilon r? So these questions might come in your MCQs also, right? It might say that what is the associated quantity with the dielectric constant. So it might give you the options: relative permittivity, right? Absolute permittivity, right? What is that? So you should be knowing the dielectric constant is relative permittivity, right? Then Coulomb's law statement you must learn, you must remember. What is the value of K? You must be knowing, right? With SI units, you must be writing. Units are very important. All right. Right. Then I have written a Coulomb force in vector form, right? It is written in NCRT also. You can refer to other materials also, which you have gone through in your uh, classes with askIITians or your school, right? So you must be knowing this representation, Coulomb's law in vector form, right? Okay. So these diagrams is also associated with the Coulomb's law in vector form. So this is important, right? Then electric field's definition, unit of electric field, electric lines of force, the properties of electric lines of force, that electric lines of force cannot intersect and all, right? Then we have these properties I was telling about, these diagrams, right? These diagrams are for like charges. This one is for dipole. So both these diagrams are important, right? This same diagram will be there for two negative charges, but the arrows directions would reverse them, right? The electric field intensity due to a point charge. Then this question sometimes come, right? Electric field due to ring of uniform charges. So what is this formula, right? You might be knowing
So
this.
this is the
You
same
must have
as
done this in your
magnetic field at axis
same,
of the
same,
circular.
right,
Yeah.
same. It is
Okay.
the same. So it will not ask you the derivation of it, but yes, you must be knowing the formula of it, right?
Yes, sir.
The electric field due to thin spherical shell, right? You should be knowing that the electric field inside a thin spherical shell is zero, right? And what is it at the outside, right? These diagrams are important. What is Gaussian surface? That is important. You should be knowing that, right? The electric field of this one I was telling you, I have put it down in the notes because you must have done it, but this is not in your CBSE syllabus. They have not written it. That non-conducting solid spheres electric field, they have not written. But yes, you must be knowing it, right? I am supposing that you must be knowing it. If you do not know it yet, no need to know now, right? This is non-conducting one. You have charge inside the sphere also, right? All right. Then this is for infinite length. This formula you might be knowing, lambda by 2 pi epsilon naught r, right? This for an infinite length. This diagram only you'll draw. This is from NCRT only, right? Then electric dipole. What is dipole moment, right? And all this dipole moment's definition is important. What is the direction of dipole moment? Can you tell me what is the direction of dipole moment?
From positive charge to negative.
No. It's from negative charge to positive charge. Yes, Jasim,
Okay,
good.
sir.
Right. Then we have electric field due to electric dipole, right? This is due to axial point, right? So this derivation I'm talking about, right? This derivation is important. Then equatorial line, this derivation is important. These are the diagrams from the NCRT, and you must be drawing it, right? So you must be writing these derivations again and again, 2 times, 3 times. Then we have this torque, right? This one is important, P sine theta. Derivation also will come. The derivation also comes sometimes of the torque, right? How you get this P sine theta, right? Then Gauss theorem, this is for a point charge, this diagram. Then we have electric field due to infinite non-conducting flat sheet. This I was talking about, sigma by 2 epsilon naught, right? Its derivation might come, right? Right. Then electrostatic potential and capacitance, you see we have these potential minus dV by dr, electrostatic potential, right? What is equipotential surfaces, potential energy, capacitor, all these topics we have, right? So what is electric potential, you must be knowing, right? What is the potential difference, how it is related to the work done and all, right? Then potential due to a point charge, what is the relation between electric field and potential, this is important, minus dV by dr, you must be knowing that, right? Okay, can you tell me in which direction electric field is always there? In the direction of decreasing potential or increasing potential? In which direction electric field is always, what is the direction of electric field? Yes, good, Jasim. It is in the direction of decreasing potential, right? This is the direction of, that is why there's a negative sign here, right? Then your potential due to several charges, again the superposition principle. Then potential due to charge spherical shell. As we have derivations for electric field, right? These might also come, right? I have not mentioned them because it's not in your NCRT, right? But you might be knowing it, right? How we calculate the potential due to a charged spherical shell, right? How it is constant inside the spherical shell. So potential is constant inside the spherical shell up to the surface, and up to the center of the spherical shell the potential remains constant, right? Then non-conducting sphere you need not worry about, right? Then what is the common potential? This question generally comes. That is, what is the common potential when two spheres are joined by thin wire? Right? You give you give charges to one sphere Q1, you give charge to another sphere Q2, and then you join them by conducting wire. The charges will get transferred, and what is the common potential they attain? This question generally comes, right? So this you must be knowing, right? So I've written down the important key concepts you must be revising, right? So then we have potential at any point. That's what I'm telling you. This derivation you'll learn of the axial line, of the equatorial line, but this derivation you need not learn. Just you need to know the formula part, right? This ones, that it is P cos theta by, yep, Kp cos theta by r square, right? Only formula part you should be knowing. And then this questions, this is a typical question which sometimes come, not always, but sometimes come. So if you have an idea of solving this question, you must revise it, right? Again. So if n drops coalesce to form one drop, right? What is the potential that becomes then, right? So that you must be knowing, right? Then electric potential energy part we have, right? Electric potential energy of an electric dipole in electric field, right? This I was telling, right? So this you must be knowing. Then capacitance, capacity of isolated spherical conductor, just the formula part you should be knowing, that it is 4 pi epsilon naught r of an isolated spherical conductor. But otherwise, the important aspect from this is the parallel pit capacitor, right? The potential energy associated with it, right? And then the energy density, it is half epsilon naught E square. You must be knowing it, right? So this will be shared, right? And this one's about the electrostatic potential, right? This one is about the equipotential surface. This is the equipotential surface. Then this is the series combination. Can you tell me what is the equivalent capacitance in a series combination? If I'll say what is the equivalent capacitance of series, it is 1 by C1 plus 1 by C2 up to 1 by Cn. Right? Good, Jasim. Right? And what about the parallel one? If C1, C2 is there, so C parallel becomes, we add it. It is C1 plus C2. Right? So this you must be knowing. Yes, good. All right. I'm just summing it up, right? So we are short of time. So then force of attraction also sometimes come, but if you have not read it yet, you need not, not very important. This might come that there are two plates of a charged capacitor. Then what is the force of attraction between them? So there's this formula involved here. So this is important from the competitive point of view, but in CBSE they might ask, or so if you know this, it's good. If you don't know this, need not worry about it. Right? Then we have current electricity. You see, so potentiometer is not there. Meter bridge is not there, right? Only Wheatstone bridge, Kirchhoff's laws, cells. The cells part is very important, right? So current, then drift velocity. You should be knowing drift velocity. I have told you, right? These formula you must be knowing, right? These formula I have written that this rho is. You see, I have told you this relax that in conductors. What happens? Resistivity increases on increasing the temperature. You see, I'm just why I've said you that resistivity increases because relaxation time decreases. Right? Tau is what? Tau is the relaxation time. It decreases because the motion becomes more random. Okay? As it decreases with increase in temperature, as it is in the denominator, resistivity increases. Get it? Right. So these formula are important. Then we have temperature variation, right? These formula, sometimes numericals, MCQs will form from this temperature dependence, right? RT is equal to R naught 1 plus alpha delta T, right? Then resistivity of formula. Then you have current density. These are all formula involved, right? With respect to current density, electric power, right? So J is equal to NEVD, J is equal to sigma E. This form of Ohm's law. Sometimes it might ask you as they ask you Coulomb's law in vector form, they might ask you Ohm's law in vector form. Because current density is a vector quantity, electric field is a vector quantity. So this is Ohm's law only, but in vector form, right? So you
Yes.
right. So you should be saying that vector J is equal to sigma vector E. So this is the Ohm's law in vector form, right?
Yes, sir. Sir, sigma is the conductivity, right?
Sigma is the conductivity here, right? Right. I can write in the form of resistivity also. If I'll write vector E is equal to rho J, right?
Yes, sir,
Then it will
Roger.
become in the form of resistivity. Then
Yes, sir.
resistance in series, resistance in parallel. You already did it in many times, 8th, 10th, right? This part is important, right? This parallel parallel cells, right? This series cells. This part is important. How to find? So I'm telling you that if you're comfortable, you should learn the derivations also of them. That how we get it, how that formula we get it, right? So let's say we have this, no. Let's say I have these. This is in series, right? This is in series. E1 and E2 are in series, right? And let's say the internal resistance is R1 here, R2 here. So what is the R equivalent? Can you tell me what is the R equivalent here? R equivalent is R1 plus R2 only. And in series, what is the E equivalent? You need to see the polarities now, right? As they are in the same way arranged, right? It is positive here, negative here, positive terminal here, negative terminal here. So I'll just add it. E equivalent would be E1 plus E2, right? Good, Jasim, right? It is E1 plus E2. Right? E1 plus E2. In parallel, what happens? Because the cells are in parallel, so resistances are in parallel, internal resistance in parallel. So 1 by R equivalent will become what? 1 by R1 plus 1 by R2. So it is so sorted, right? What is the equivalent EMF here, right? So it becomes E equivalent by R equivalent is equal to E1 by R1 plus E2 by R2, right? So how do we arrive at these formulae? If you're comfortable, you please practice it, right? The derivation part of it also you practice. If you're not comfortable, just remember the formula, right? Then we have this Wheatstone bridge. Lastly, I'm discussing the Wheatstone bridge. So what is the concept of Wheatstone bridge? Can anyone tell me? What is concept of Wheatstone bridge? Right. So this form of arrangement, right, is known as Wheatstone bridge. This form of arrangement of resistors. So here we have a here we have an arm, right? Galvanometer arm. It is known as galvanometer arm. So when this ratio, when R2 by R1, let's say it is R2, it is R1. So when R2 by R1 becomes equal to R4 by R3, right? These resistors ratio, or I can say this way also, that R2 by R4 becomes equal to R1 by R3, right? This way also I can say, if the ratio of these two resistances is equal to ratio of these two resistances, then we say the Wheatstone bridge is balanced. And what do we mean by Wheatstone bridge getting balanced? We mean that there is no current through this galvanometer then. There will be no current through this arm. If there is a resistor connected here also, then we can remove that resistor, right? So this is the main concept of it. And why do we use it? We use it to calculate the value of an unknown resistor. If I know the value of, let's say, R1, R2, R3, and I want to know the value of R4, I can calculate by this formula, right? Right. So this is all about the Wheatstone, which you should be knowing, right?
Okay, that is 4 times 9.
So I think that's all, right? That's all. I've made you revise like
Sir, the most important derivation from this chapter would be the proving the principle of meter bridge via Kirchhoff's law, right?
meter bridge is not there. No, meter bridge is not there in your syllabus.
Sir, but in our pre-boards, that kind of question came. Like we have to prove the Wheatstone principle in the meter bridge using Kirchhoff's law or something.
That is how much? That is also 36.
That might be possible that in pre-boards they have given, but in the now this year they have not given meter bridge. But if you know, no, if you know the meter bridge, then you you keep that idea, right? You
Yes,
do
sir.
not
Okay.
leave it then. But now it is not written in the syllabus, right?
Okay, sir.
Yes, meter bridge is a Wheatstone bridge only. The Wheatstone bridge principle is applied in the formation
Meter
of
bridge.
meter
Yes,
bridge.
yes.
Right. It's easy. Meter bridge is easy. Potentiometer is complex, but meter bridge is
Sir,
easy.
but potentiometer is deleted now.
Potentiometer is not there. Potentiometer is not there. Right. So derivation, if the cells one, the combination of cells, you please just have an idea about it. And I don't think nothing else. Then the Ohm's law wala part, right? The Ohm's law, the J is equal to sigma E, right? How that comes, right? How can we rearrange those formulae, right? J is equal to anybody. How can we rearrange those formulae? How can we manipulate those formulae? That you must be keeping in your mind,
Okay, sir. Okay, sir.
right? So anything else, the team will share this PPT with you if it will be helpful for you, right? So I think the session have been helpful to you in just remembering, just going through the for at least the topics you need to cover, right? So if you have any question, right, you please you can be in the meeting, right? We have a webinar tomorrow also, right? Tomorrow I'll be discussing the magnetism part, right? The moving charges and magnetism. So the same concept I'll be applying. I'll try to, because 1 hour is not sufficient, I think. So I'll try to put some
Yes,
previous
sir.
year, I'll try to put some previous year questions also. But I think that now attending this webinar, you should be reading about previous year questions, right? You should uh, at least download 2024 25 previous year paper and
Yes,
just
sir.
look
I'm
at it, right?
solving those daily, sir. Previous year questions.
That would only helpful, right? And just revising the theoretical aspects and the derivations, theoretical, and practicing the numerical from the previous year papers only now at this point of time. And the notes, whatever notes you have from your classrooms and your tuitions and coachings, right?
Yes, sir.
All right, participants. Thanks a lot for attending this webinar, and I'll be expecting you tomorrow also, right? So I think it will be helpful to you. So thanks a lot. If you have any other question, I'm there for you. Right. Thank you.
Thank you, sir. Bye, sir.
Bye. Bye.
Okay, sir.
One minus root of is not a possibility, right? So that value will be minus 1 plus root 6y plus y is only possible